My name is Hunter Manning, and this is my submission for Lab 4, Physics 2. Today we'll be discussing magnets. So for this lab, there were three main purposes. The first being to measure the distance dependence of the magnetic field from a bar magnet and compare these measurements to the distance dependence predicted by the Biot-Savart law. The second purpose was to calculate the experimental value of the bar magnet's magnetic dipole moment. And the final purpose was to create a computational model to visualize the magnetic field of a magnet on and off axis. Moving on to the core concepts and fundamental principles of this lab. Similar to an electric dipole, which point from negative to positive, bar magnets have a magnetic field that points from south to north. The Biot-Savart law was used to calculate the magnetic field using the equation below. This law can then be related to the distance dependence of the magnetic field of a bar magnet, as seen in the equation on the right. And this equation may then be linearized and graphed, which I will discuss later in the report. Briefly touching on the primary results of the lab, the slope due to linearization was found to be negative 2.3. Further, the magnitude of mu is approximately 5.1 am squared. So for the experimental setup for this lab, it was done in two parts, an on-axis part and an off-axis part. The first part was the on-axis part. So first, we compensated for the magnetic north by rotating the phone until the magnetometer gave us an x component of 0. The second step we did was to find the magnetometer chip in the phone, and the final step was measurements. And in this, we slid the phone along the x component to find a given value, and then we recorded that distance. Once we finished this, we could move on to step 2, which was the off-axis setup. First, we found d perp. Then we recorded the y component of the Earth's field. Then we found d by moving the phone up and down by d perp. And the fourth step was to determine the x, y, and z components of the net magnetic field. And the final step of the off-axis part was to correct for Earth's magnetic field. As for the assumptions made in this lab, there were two primary assumptions. The first being that the bar magnet can be treated as a magnetic dipole, and the second was that the only magnetic fields are from the Earth and the bar magnet itself. The system and the surroundings could also be identified in this lab. The system can be identified as the bar magnet, and the surroundings can be literally everything else. Moving on to the observations and data, below is the data we gathered in this experiment. Based on this data, our expectations were confirmed that the magnetic field would be stronger when the magnetometer was closer to the magnet, and this magnetic field would drop off as distance increased, as you can see in the negative slope. Moving on to the calculations. Using the equations that we discussed in the core concepts section, we can find the magnetic dipole moment. First, we must solve for r, and in our case, we had an r value of around 0.36. From the linearization of the data that we found in the graph, k is roughly 2.1 times 10 to the negative 6, and the y-intercept was found to be at around negative 13.1. Further, the slope was found to be around negative 2.3. These were all found by calculating the value of E raised to their respective values in the graph. And finally, the equation can be rearranged for mu mag. This allows us to plug in our values that we just discussed to find the magnitude, and this gave us a magnitude of around 5.1 am squared. So moving on to the code. GlowScript was used to create a computational model for the experiment. Mu mag was entered at 5.1 based on the calculations from before, and the equation used to solve the magnetic dipole was included. I also created observation points that were on-axis and off-axis, which we'll use later. The on-axis points and their corresponding code and arrows are seen on the left. I did the exact same thing for the off-axis values, which are inputted on the right. I'd now like to discuss the results of this coding. The magnetic dipole moments are seen in the arrows below. In the orange arrow, you can see the magnetic dipole moment of the on-axis field. In the blue arrow, you can see the magnetic dipole moment of the off-axis field. And up there in the top right corner, you can see the magnetic field of the 45 degrees from axis. Their corresponding values and magnitudes are also seen below the image. I now want to take just a second to compare the results and discuss some potential sources of error. So, as you can see, the experimental computational values did not result in the same values at all, and they're actually quite different. The experimental value is calculated as the average of the B net, while the computational value is derived from the calculated magnetic dipole moment. And some sources of error that could have contributed to this are the presence of other magnetic fields, which we did not consider. There was also probably some inconsistency with the angle of the phone, because we didn't always have it at the exact angle it needed to be. And the final potential source of error is that there could have been some inaccuracy and inconsistency with the magnetometer. And to wrap this report up, I'd like to take just a second to answer the two what-if questions. For the first what-if question on the left, the values would have been dramatically different, as finding any value becomes significantly more complicated. However, these values can be easily achieved if we do know the angle from the north. And for the second what-if question, the combination of the magnetic fields would be in the same direction but just be much stronger. Thank you. Have a good day.